So now we know, given a policy pi, right, how we can compute the value function for that policy pi. Right? So what does the value function tells us? Value function tells us what is the total expected return, right, you are going to get starting from a state S and following policy pi, right. So given a policy pi, we know how to compute this V pi either by using the Bellman equation and solving it as a system of linear equations, or by solving it in some kind of an iterative fashion, right. So we will see that in a bit, right, how to solve this as an iterative example, and we saw an example of how to do this in this very simple grid world. So given a pi, we know how to find V pi, right, but that is not what we have set out to solve, right. What we want to solve is what is the best possible way to behave in this MDP, right. So we want to find out what is the best possible way to behave given an MDP, right. So that is what would constitute a solution to the MDP that you have. So remember, you start with the word problem, you convert that into an MDP with states, actions, rewards, and transition probabilities and all that, and then you try to solve for that, right. So as an intermediate step to solving it, we have looked at how we can find the value function V pi, right. So now we want to solve the MDP. So what does solving it mean, right? The first thing I want you to note is that for finite MDP, so for infinite MDPs, there are certain other technical conditions, we will not think about it. So we will talk about finite MDPs, right. So for finite MDPs, so the policies can be partially ordered. Policies can be partially ordered. So what does that mean? So I will say that pi is greater than or equal to pi prime. Pi is greater than or equal to pi prime if and only if V pi of S is greater than or equal to V pi prime of S for all S. Okay. So what do I mean by that? So the first thing I am doing is, for comparing policy pi and pi prime, I am going to compare the value functions of the two policies, right, and I am going to look at that in each and every state. So if in state 1, V pi should be greater than or equal to V pi prime of state 1, right. So let us say there are, just giving you a simple example, let us say there are like 4 state MDP, just to, for simplicity's sake, makes it easier for me to draw, right. So let us say that this is V pi, right. So I say this is 0.3, 0.6, 0.6, 0.9. This is 0.1, 0.4, 0.8, right. Let us say that's my V pi and this is my V pi prime, right. So if you look at it, there are 4 states here and I can compare it on each of these 4 states. So this is, let us call this 1, 2, 3, 4. So V pi of 1, right, is 0.3, V pi prime of 1 is 0.1, that is correct. So in state 2, V pi is 0.6, V pi prime is 0.4, right, and in state 3, V pi is 0.6, V pi prime is 0.4, and in state 4, V pi is 0.9, V pi prime is 0.8. So that means V pi is greater than or equal to V pi prime in all the states, right. In such a case, I will say that pi is greater than pi prime. Notice that the equal to has gone here, right. Suppose it had been something like this, right. So let us say in this state I had 0.9, then I would have said pi prime, right. Because in that state V pi is equal to V pi prime, right. Therefore, I would have said pi is greater than or equal to pi prime, right. So this is not clear. So so we will leave it at this, right. Pi prime is greater than or equal to pi is greater than or equal to pi prime. Suppose it had been the case that this was 0.7. You get that? So that is 0.7. So what happens is, in 2 states V pi is greater than V pi prime, right. In one state they are equal, that is okay, and in one state V pi prime is greater than V pi. Then I can't compare pi and pi prime, right. So what I have done so far is only if they are equal for all states, right. That is why this is a partial order. So there might be cases where for some states pi is better, v pi is better, for some states v pi prime is better. In such case, these are not comparable. I can only say that there is a partial order to this, right. So, I hope that idea is clear. So, now we have this notion of a partial order. So, given that it is a finite MDP, so what is a finite MDP? So, finite MDP means there are a finite set of states and a finite set of actions, right. So, you can always think of, you can determine a finite set of deterministic policy, right. You can define a finite set of deterministic policies on these MDPs. So, that is something to keep in mind. So, there are a few statements that I am going to make, right, which I will make without proof now, right. So, we will give you videos that you can look at to see some of the proofs, but they are not really part of the actual lecture. I do not expect you to understand the proof. This is only for you to look at if you are keen on the proofs, right. So, the first thing I am going to make is that there is at least one policy, right? There is at least one policy, right, in this finite MDP such that I can say that this policy pi, we will call it pi star, right, is greater than or equal to pi for all pi that I can define. Okay, does it make sense? So, we said pi is greater than pi prime, greater than or equal to pi prime if this condition on the value function is satisfied for all states. Now, I am saying that there is at least one policy which we will call pi star, right, that is greater than or equal to pi, right. So, for all pi. So, obviously, it holds for pi star, in which case it is actually equal, but for any other policy that you pick, right, pi star is better than that policy or better than or equal to that policy. Right. So, I am saying that such a pi star exists for finite MDPs always, right. So, that is the one statement, that first statement I am making, that you have to take on faith, right, that there is a pi star that exists such that pi star is greater than or equal to pi for all pi, the first statement I am making. The second statement I am going to make, again without proof right now, which I want you to accept, is that there is at least, I mean, we said now there is at least one pi star, right. Now, I am going to say there is at least one deterministic policy, right, that is optimal. Right. So, that means that there could be many pi stars, that is what we say here. We denote all the optimal policies, right now we denote as pi star, it could be any one of those optimal policies, we do not care. But among these policies that are optimal, there is at least one policy that is deterministic. So, that is the second statement that I am going to make. These are useful things for us to know when we are actually building the algorithms for solving these problems, because we will put these things together to solve it, right. So, there are many policies, right, possibly many policies that are better than or equal to all the others. So, I will come to that in a bit as to what it means. Let's show that, right. Let's look at this, right. Let's take an example. So, here is an example. So, I have an MDP, right, the same grid world setting that we looked at earlier, right. So, I have the cells or the states, the actions are north, south, east, west. For the time being, let us assume the actions are deterministic, you always go in the direction you intend to go, and there is a transition probability P and the reward R, right. So, what do you think would be an optimal policy in this MDP, right? Let us say that I give you a reward of -1 per time step, right. You have a reward of -1 per time step. So, what will be the optimal policy in this MDP, right? That is one optimal way. So, you can start from the start state, go up, right, and go right, up, right, up, right, up, right, up and right, okay. So, that is basically it. But what if instead of going up, I go right here, right, that is also possible, right. There are, so this red one also shows a optimal execution, right, but that is not it, right. This green one also are optimal. So, there are many optimal ways to reach from this state to the goal, right, and each one of them gives you a different optimal policy, right. So, you could either go up here or you could go right here or east, right. You can either go north or east, right, and you have an optimal policy. Likewise, you could go like east or north here. Here you have to go north, here you have to go east, but you could go north or east in each one of these states and you will reach that, right. So, there are many such examples here, right. So, there are many possible optimal policies, even deterministic optimal policies, right. That is one thing to think about. So, I can go like this, like this, like this, that is one optimal policy. I can go like this, like this, like that, that is another optimal policy, and both are deterministic. I am always going north in the first state, I am always going east in the first state in the two different policies, but they are both optimal, right, both deterministic and optimal. Now, if I start looking into stochastic policies, right, then with some probability I can go north and some probability I can go east, that that can still be part of an optimal policy, right. So, it becomes very crazy. So, if I go, say, I toss a coin, if it's heads I go north, if it's tails I go east, right. So, with probability 0.5 I could do that, or with any probability 0.9 I can go north, probability 0.1 I can go east, right, as long as the rest of the policies are all satisfied, right? So, I can have an infinite number of optimal policies. So, that is the thing to remember. I can have an infinite number of optimal policies when I am starting to look at stochastic policies. So, now, given that there are so many different solutions, how do I actually solve the problem, right? The thing is, even though there are many optimal policies, right, there is only one optimal value function. So, how is that? So, let us take this, right. Let us say if I go up, let us take the blue, let me go back a few steps, right. Let me take the blue policy, right. So, the blue policy, what is the reward that you are going to get? Okay, I get a -1 for this, -1, so the -2, -3, -4, -5, -6, -7, -8, -9, -10, -11, -12, -13, -14. So, for this I get a reward of -14, right, total return, right, this is the return I get is -14, right. Likewise, let us look at this one, right, let us look at this one. So, again, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, for this also GT is -14, right. So, the return you expect is -14. Remember, there is no stochasticity, the actions are deterministic, the policy is deterministic, the reward is deterministic, and therefore, this is basically the return, right. I mean, there is no expectation that you have to take, right, in this particular simple example. So, all of these have reward of -14, and each one of these green policies also have -14 as the total return. So, if you actually stop and evaluate the policies, the value functions of these policies from anywhere, you will find that the return is the same, right. Therefore, right. Therefore, you have a situation where there could be many optimal policies, but only one optimal value function, right. So, let us go back, I need to go back to the previous slide, apologies for this. So, now remember that we said pi star is greater than or equal to pi for all pi. Now, I am going to say the following, right. So, for each of these pi there is going to be a v pi of s, right. So, for each of these pi there will be a v pi of s, then v star, right, the policy corresponding to v pi star, right. So, this v star is essentially v pi star, right. So, v pi star is going to be max over all pi, that is basically the best over all policies of v pi of s. So, for each state s, right, for each state s, I am going to look at all possible policies that you have. For each state s, look at all possible policies and take whichever policy has the highest value in that state, assign that value to v pi star, right. So, v pi star is what we are denoting as v star, right, remember that. Similarly, q pi star is what we are denoting as q star, right. So, just remember that, right. So, for every state s, we look at all policies pi, right, take whichever is the maximum among that pi and assign that value to v star, right. So, this makes intuitive sense, right. So, why does it make intuitive sense? We say that pi star is greater than or equal to pi for all pi, right. We say pi star is greater than or equal to pi for all pi, okay. That means that v pi star of s is greater than or equal to v pi of s for all pi, right. So, I am just flipping it around and saying that, hey, since by definition this is what should hold, so I am going to say that v pi star of s should be max over pi v pi of s, otherwise pi star can't be greater than or equal to all pi, Does that make sense? If pi star has to be greater than or equal to all pi, then the value function of pi star should be greater than the value function of pi of s, right? For any state s, for value function of pi star should be greater than value function of pi, right? Now, for that to hold, then value function of pi star should be the highest among all possible policies pi for that state s. So, we do that for all states, right. So, this is basically how we define something called a optimal value function, right, and this optimal value function is unique for an MDP, right. Optimal value function is unique for an MDP, and therefore, many solution approaches, right, instead of trying to find an optimal policy, try to find an optimal value function, because the solution is unique. So, there is a single target that you are trying to compute. So, you try to compute the optimal value function, right, try to compute the optimal value function, and from there you try to derive the optimal policy, right, try to compute the optimal function, from there you try to derive the optimal policy, right. So, just like we did for V star, we can also write an expression for Q star, right. So, what is the expression for Q star? So, instead of for all S, we will say for all S and all A, right, Q star S comma A is equal to max over pi Q pi S comma A. Is it fine? So, you have your optimal policy, right, you have multiple optimal policies pi star, but what we are claiming is that all the policies pi star are going to have the same optimal value functions, whether it is V pi star or Q pi star, it will be the same value function for all the optimal policies, right. So, what we mean by all the optimal policies, right. So, we looked at multiple examples here, right. Each one of these policies is a pi star. Each one of the policies that we have here is a pi star, and therefore, we can write the value function as V star of S equal max over pi V pi of S. This is for any pi star. This holds for any pi star, not just for one pi star, it holds for every pi star. Likewise, we have a definition for Q star SA. So, I hope this is clear so far. Okay. Now, we have to start talking about, hey, how do I find this V star and how do I find this Q star, right. So, now what we can do is we can go back and try and write a Bellman optimality equation, right. We wrote one for V pi, right. We wrote a Bellman optimality equation for V pi, right. Now, we can try and write a Bellman optimality equation for V star, right. We can write a Bellman optimality equation for V star, right. So, this is the derivation. We are starting with one very a cool observation, right. So, this is by definition, this has to hold, the first line has to hold by definition. So, what does it mean, right. So, we say that V star of S is equal to max over A, that is max over all possible actions I can take in state S, Q pi star of S comma A. What is that? So, Q pi star of S comma A is what? Remember, by definition, what is Q pi star of S comma A? It is the expected return that you will get if you start in state S, do action A, and after that you do policy pi star, right. So, if you remember earlier we had this, right, Q pi SA, you start from state S, you do action A, and after that you follow policy pi. Likewise, from state S, you do action A, after that you follow policy pi star, which is the best possible way that you can behave, right. So, pi star is the best policy, you follow that after take action A, okay. Now, V star of S is the best possible return that you can get starting from state S, right. So, and so obviously, even though from the next state onwards you are doing pi star, in the state S you should be doing the best possible action, so that overall your return is as high as possible, right. So, you can see this, right. So, overall the return has to be as high as possible. There are multiple initial actions that you can take, but you want to take that action that gives you the best possible Q star or Q pi star from starting from state S. So, by definition, I have to have my V star of S equal to the best action taken from state S following policy pi star after that, right. So, this is by definition, right. And what is happening in the next step, from here to here, again is the definition of Q, right? We already looked at definition of Q pi, this is the definition of Q, right? So what we have done here, so this is GT, which is the return that you get starting in state S, taking action A as your first action and following policy pi star thereafter, right? If you remember in Bellman equation, we said you will follow policy pi, now we have to say you are following policy pi star, right? Now again, just like we did in the last time, I can take GT and I can write it as RT plus 1 plus gamma GT plus 1, right? What is GT plus 1? It's a return starting from the state at time t plus 1, right? So I don't know what is the state at time t plus 1, but the return starting from the state at time t plus 1, right? Now what I can do is I can take this expectation and simplify it a little bit, right, by pushing this expectation over pi star, right? This expectation over pi star that I have, I push it into the G, because this RT plus 1, right, RT plus 1 is conditioned on ST equal to S and AT equal to A and ST plus 1 equal to some whatever, right? Right. So in none of these does pi star appear, right? This is fixed, and this comes from my P, right? P of my MDP, right? So in none of these three terms is pi star playing a role. Therefore, RT plus, the expectation of RT plus 1 doesn't have to be taken over pi star, right? It is only the GT plus 1 where pi star plays a role, remember? So from ST plus 1 onwards, I am taking actions according to policy pi star, right? So that is exactly where the pi star expectation plays a role, right? So I take the expected value of pi star of GT plus 1, right? Now what is the expected value of pi star of GT plus 1, which is basically V star of ST plus 1, right? V star of ST plus 1. So now I can simplify the whole thing and write this expectation is just over P now, right? This expectation is just over P because the pi expectation has now been pushed into the V star. I can take this expectation, simplify this. So sum over all possible S, all possible R. So probability of seeing that S prime and getting the reward R, given that I started in state S and took action A. So that's the part here. So this RT plus 1 in this particular summation term has a value R, and this ST plus 1 in this summation term has a value S prime, right? So basically I can write this. So this is V star of S, right? So this is basically how I derive the Bellman equation, right? Bellman equation for V star, or sometimes we call it as a Bellman optimality equation for V star. Okay. Take a deep breath and try to follow what we did. It exactly mirrors what we did for V pi, right? Exactly mirrors what we did for V pi. So take a deep breath, compare it to the V pi derivation, and then try to understand what we did in V star, right? Okay, good. So likewise, just like we wrote a optimality equation for V star, we can write optimality equation for Q star, right? So what is optimality equation for Q star? So you have to think about you have to think about the steps that we have to look at here, right? So you have taken action, when you are in state S, okay, you have taken action A, so you are going to get reward RT plus 1, right, and then you are going to go to state S prime or ST plus 1, right? You are going to go to state ST plus 1, and from ST plus 1 you are going to behave optimally, right? From ST plus 1 you are going to behave optimally, right? So what does that mean? From ST plus 1 you should get V star of ST plus 1, right? Right, you should get V star of ST plus 1, right? So that's basically what it is, right? So the max A goes away because you already fixed your A, so you have the expected value of RT plus 1 plus gamma times V star of ST plus 1. But we know what V star of ST plus 1 is. It's basically max over A Q pi star of ST plus 1 comma A, right? So that's basically what we are writing here. So it's max over A, because A is already fixed, we say max over A prime Q star of ST plus 1 comma A prime, right? So this is actually equal to V star of ST plus 1, right? So that's V star of ST plus 1, and we are writing that out like this. And now once we have this expression, we can go ahead and write out the expectation. So everything looks the same, right? What is the difference between the V and the Q equations? V, the max is here, right? We will have a max over A here, right? In Q, the max comes inside into the Q function itself, because you want to figure out what is the value of the next state. So you do that by pushing in the max here and taking the max over Q. So now you can write Q star in terms of Q star instead of writing it in terms of V star. You can write Q star in terms of Q star, and in the previous Bellman equation you have written V star in terms of V star. So basically you have both your optimality equations set. So what is the use of this optimality equation, right? So let us say that I have my V star, right? My V star has been learnt, it is all ready. Okay. So now any policy, right, that is greedy with respect to this V star, right? Any policy that is greedy with respect to this V star. So what do I mean by that? So let us say that so I am in this state, right? I have 4 possible actions I can consider, right? I have 4 possible actions I can consider. Now each one of these actions is going to take me to a potential next state, right? So if I go here, I land up here. If I go here, I land up here. If I go here, where will I land up? In the same state. And if I go here, I land up in the same state. So there are four possible actions and 3 possible outcomes, right? Now let us say the value for this state is 14, and this is 14.3, and this guy is 13.8, right? Now what will happen? And each action gives me a -1, right? So if I go up, I will get -1 plus 14. If I go right, I will get -1 plus 14.3. If I go down or I go left, I will get -1 plus 13.8, right? So this is the reward, this is the return I am going to get. I am just looking one step ahead, right? I am just looking to the next state and figuring out which one is better, right? So which one is better among these? So this is better, right? So the -1 is common, so I can kind of ignore that. So this is better, and therefore the optimal policy for me is to go to this state, right? So that's basically what we mean by saying that you are greedy with respect to V star, right? So greedy with respect to V star means, okay, I have my V star computation done, so I end up with this is 14, this is 13.8, this is 14.3, and then when I want to pick an action to move, or when I want to pick an optimal policy, right? I need to pick an optimal policy. That's the goal of solving an MDP, right? Picking an optimal policy. When I want to pick an optimal policy, I just look ahead one step on the value function, right? On the optimal value function, right? And then that gives me the optimal policy, right? Suppose this had also been 14.3, right? So what would have been the case? Then this or this would have been optimal, and I could have taken any one of those actions, and that would have been an optimal policy action in that place, right? So going back to our grid world, remember this AB grid world that we talked about after the Bellman equation example for V pi. So I'm not going to do this right now, but this is V star, right? This is the solution for this after I have solved the problem, because I have not told you how to compute V star yet, but this is the V star. Okay, let's look at this. Now what this means is, suppose I take a state here, right? Let's take this state, right? So what is the optimal action? I do a look ahead, right? So 1 gives me 17.8, 17.8, 14.4, 14.4. So I could either go up or I could go to the left. Both of these are optimal actions in this particular state. Let's take another state. Let's take this guy, right? Now what about this one? Well, the 17.8, 17.8, 17.8 and 22. So obviously only going up, right? So as you can see this, in all the states in this line leading up to A, the best policy is to go up, right? And in every other state, the policy is to get to as close to A as possible, right? Except in the state where you are happy going to B. Does it make sense? So if you have V star, you can do this one step look ahead, look at the neighbors that you can reach by doing one action, just one action, and figure out what the values of those states are, and whatever is the highest there, you pick that and then take that as your action. Now, we are talking about deterministic policies, if deterministic outcomes, right? If there are stochastic outcomes, then you'll have to do what is the expected return that you are going to get. So, for example, let's say that if I move up, right, I could end up here or here or here. If I had this kind of a dynamics, right, then for doing the one step look ahead for the action up here, I will have to look at, okay, what is the probability of getting 19.8, right, and then what is the probability of getting this 17.8 and this 17.8, take the expectation, take the average of those values and use that as my value for going up. Okay. So, this becomes clearer as you actually work out an example that you would do in the tutorial later. Okay. So, that's basically why you need to find V star. Once you find V star, you can write a optimal policy pi star. So, what about Q star? Right? Q star is even better. Why? Because I don't even have to do a one step ahead search, right? I don't even have to do the one step look ahead because I already have the Q values of the action. So, when I am computing the Q star itself, I know that the first action I take is A, right, and then I am going to look at what is the future action to take, right. So, I don't have to go ahead, right. I don't need to know what is the next state I am going to land in. Right? I can just look at what are all the values for the actions, right. I have 4 different actions. I look at what are all the values for the action. Whichever action has the maximum value, I'll take that as my policy action, right. So, it's even better than the state value function. The state value function, I have to do a one step look ahead. I need to know what are all the states I'm going to land in and look at the values of those states, and if the outcomes are stochastic, and then I have to look at all the possible states I could land in, take the expectation and all that, right. But the Q values, if I'm learning the Q values directly, I do some of this computation while I learn the Q value itself, right. And if I give you a way of learning the Q values, once you have it, I don't have to even do a look ahead on the next state, right. I don't need to do this one step look ahead search. I can just look at the Q values in the current state and pick the action with the maximum Q value and I am set. Okay. Make sense? I just look at the Q values in the current state, take the action with the maximum Q value and take that as my policy pi star. Okay. So, why is this useful? Later on, when we are actually talking about reinforcement learning methods, right, we will be looking at domains, we will be looking at problem settings where we don't have access to P and R, we only have access to those samples. Remember I was telling ST, AT, ST plus 1, AT plus 1, that sequence of samples that you get, right, you only have access to those samples. You don't have access to P, you don't have access to R. So, you can try to find P and R, right, from those samples and use that to learn. That is a perfectly valid way of solving the problem, or you could just directly from the samples try to find out what Q star is, as we will see in the later methods that we look at, right. So, if you are able to estimate Q star without knowing P and R, you can do the policy pi star also without knowing P and R, right. If you are only finding V star, you need to know the P, right, before you can find what is pi star. But if you are learning Q star, you don't need to know the P. You can directly optimize from the Q star to get pi star. Okay, so that's where we are at. Okay. Let's stop here.